Hi guys, let's talk today about the Schmitt trigger. I will start by revisiting what a Schmitt trigger is. Actually, it is a different version of a typical inverter. This is the schematic of a typical inverter. The output characteristics of a CMOS inverter looks like this. Here we have at VDD from when the input is swept from 0 to VDD, and at midpoint here we can call the switching the VM, at which V input is equal to V output. Now what happens when the input exceeds VM? The output is pulled to low, and when the input is below VM, the output is pulled too high. This happens either way, which means that if we have signal, let's say this is VM, this is VDD, V input, the output should look like this. When it passes here, the threshold, again when it comes too high, the output is pulled again too low. What's different for a Schmitt trigger? The Schmitt trigger is used to differentiate between V input high and V input low. Here, let's put some ground rules. We here talk about an inverted output Schmitt trigger, which means that is an inverter with hysteresis. So, which when we refer to V input high or V switching for the Schmitt trigger, switching point high, we mean that V output low. And when we refer to V input low or V switching point low, this means that we have V output high. Here what we want to have is slightly different from the inverter. What we require is, let's say here we have our VDD, that the output is pulled low. Okay, this is a typical inverter. Here this is VM. Here we want the output to be pulled low at some point higher than VM, which means that this is what we would call V switching point high. And what happens in the opposite direction? Now we want this point also is getting the other way around, so we'll draw another line with the arrow here, and here V switching point low, which is lower than VM. What's the purpose of this? Let's assume we have signal. This is V input low and this is V input high, and now we have our input, which is, so for a typical CMOS inverter, what's our expected output? In the beginning it should be high. Then when let's say that V input high is, for this particular case, is VM. When it crosses this point, it goes to low, and then if there's some kind of noise, small noise, it will switch again to high. Here switch to high and low and high and low until the noise is gone. What happens with a Schmitt trigger? A Schmitt trigger is triggered only in one direction, which means it will start normally here with high, and then it goes to low, but it will stay low. It will not change its state, because there is a difference between V input high and V input low, or what we call here V switching point high and switching point low. So now it will stay low until it is really the real signal goes low. Then it switches again to high. And then when it switches to high, it will not switch again to low with the noise. Otherwise, it will only switch when a real signal comes. So let's talk now mathematics. For Schmitt trigger, we can say that its V switching point high is equal to a Vm of an inverter plus delta VH, and the V switching point low equal to Vm minus delta V low. Now the delta VL plus delta VH are the noise margin. Now let's try to construct a circuit for a Schmitt trigger. I will draw first a CMOS inverter. I will try to use analogy and comparison to well understand how the Schmitt trigger is different from a CMOS inverter. For this purpose, we will use two transistors, two PMOS and two NMOS, because it will be used in the Schmitt trigger circuit. Now there's two important points here, Vx and Vy. We will see when we have the complete circuit why we use them, and also we have the normal V output. Let's call this N1 NMOS, N2 P2, this is analogous to N2, and P1. Now what happens when we have initially V input equal to 0? Of course we know that V output equal to VDD. What is important to look at is Vx. What's the voltage at Vx now? There is no current flowing through the NMOS, and they are actually two NMOS in series, so Vx voltage will be 0. As V input increases, now N1 and N2, they have similar VG, which is V input, and they have similar V source, which is ground. So their VGS is equal, which means that they will turn on together at the same time. So what will happen to switch from the output high to low? That the current at the PMOS side equal to the current of the NMOS side, which means beta, the gain factor of the NMOS side, over 2. Now we will not talk about N1 and N2, but we talk about the combination of the two, which is two transistors in series. So beta N over 2 V input. At the switching point, we know that V input equal to Vm equal to V out equal to Vm minus V threshold N square. This will equal to beta P over 2 VDD VSG, which is VDD minus Vm minus modulus VTP all square. We can see from this that we can set the Vm in the middle if we assume that Vtn equal to modulus VTP, which is somehow reasonable assumption. We can see from this that if we make beta n equal to beta p, we have Vm equal to VDD over 2. Analog design speakers like me, I don't agree that Kn prime equal to 2 Kp prime. Actually it is 3 times or maybe more, but since we talk digital, so now we can pretend that we believe that Kn equal to 2 Kp, which means that if we set Wn equal to half Wp, we will have Vm equal to VDD over 2. Now let's reconstruct the circuit to get the Schmitt trigger. What we wanted to add is 2 more feedback transistors. Again, our point Vx and the other point is Vy. Now, what happens if we have these 2 extra transistors? Let's look first at the case when V input is low, V input is 0, and V output is VDD. Now, what's the potential of Vx? Vx will have different potential. It will not be 0. At this point, Vx is N3 is on, so Vx will be VDD minus V threshold N. What happens as V input increases? If V input is increased, N1 will start to conduct current, but N2 is not, because VGS of N2 will be still not sufficient to turn the transistor on. But where the current will flow, it will flow here. We call this I1 equal to I3. So there is a low resistance path which is created by the N3 feedback transistor. So this low resistance path is taking the current which flows through N1. What happens when V input increases so that N2 turns on? At this point, the output is pulled to low. So let's mathematically formulate this. So mathematically speaking, this translates to current I1 equal to I3. I1 will be beta 1 over 2 V input, which is our point V switching point high, V switching point high, minus VTN all square. This will equal to beta 3 over 2 will be VDD minus Vx minus VTN all square. When we have switching point, this means that this point, V switching point high, is 1 threshold voltage above the source voltage of N2. So equal to Vx at this moment plus V threshold N. If we substitute here, this means that the current equal to B3 over 2 VDD minus V switching point high all square equal to beta 1 over 2 V switching point high minus VTN all square. Let's write it here. V switching point high minus VTN beta 1 over 2 equal to beta 3 over 2 VDD minus V switching point high all square. Let's have a closer look of this equation. Now what happens if we have beta 3 over beta 1 increase? This means that we have V switching point high increases towards VDD. In other words, it means that SPH, which is equal to VM plus delta VH, this means delta VH is increased. We can look at it as if we have the switching transistor. If we increase the size of this transistor, it is some kind of a resistor. So if this resistor, this is N3, if this resistor is low, this means that the current passes here in this resistor or the switching transistor, the feedback transistor, and when it passes through this transistor, this is making Vx increase slowly, which means N2 waits for a while until it switches on. If we look for the PMOS side, we have the same analogy, which means that some point we have, okay, let's do it quickly. The PMOS side, V input, and here V output. Here it's connected to ground, and here is VDD. Now this is V out, and this is P2, P1, P3. Okay, I have drawn it analog anyway. So what happens here? Here's Vy. Initially, Vy was VTP, or modulus VTP, and V input was high, let's say VDD. V output was 0. Now, what happens when V input starts to decrease? P1 conducts first, and there is a low resistance pass through P3, exactly like what happened in the pull down network. Now, at some point, V input will be V switching point low. At this point, we will have Vy conducts, which means VSG3 will be equal to Vy minus V switching point low, which is equal to modulus VTP. Now I1 equal to I3. I1, we know that it is VDD minus V switching point low minus VTP, absolute VTP square beta 1, beta 1P whatever over 2 equal to beta 3 over 2 multiplied by VSG3, which is, we have seen is, sorry, this means VSG2. I have meant this. Okay. We can say that it is for the M3, VSG is Vy minus 0, so it will be V switching point low plus VTP minus VTP, so it will be V switching point low square. So we can see a similar relationship, but in the opposite direction, which means as beta 3 over beta 1 increase, V switching point low decreases towards ground, or when the input is low, which means higher noise margin in the pull up network. Now let's take another look what happens if we have different values for the switch transistor. Here we have N3, the switch N1, N2. So let's say that N1 now will be very small size, or will have very high resistance. We know that if we remove the N3, we will reach the state of CMOS inverter without hysteresis. So how we can qualitatively explain this? As N3 size goes smaller, which means beta 3 over beta 1 is small, this means that our resistance of N3 is high. This means that when N1 conducts a very small current, even passes through N3, is sufficient to decrease the voltage of Vx. So when Vx quickly drops, this means that we have N1 and N2 with the same state, and they will conduct together. So we will reach the condition of the inverter, of the normal inverter, that we have a current passes through the B branch and the N branch. As N1 size gets bigger, this means a lower resistance, which moves the point at which the N2 is on, which means that the pull down voltage with V switching point high goes up, and we have higher noise margin. It's important to notice that there are, for the CMOS inverter, the current conducts early in the N1 and N2. This is charging the output capacitance slowly. For the Schmitt trigger, we have current passes through N3, and this current is usually takes a while until N3 is on, and the current is higher than its counterpart for the case of inverter. This causes the switching to be faster. So a typical switching waveform looks like this. Let's say that this is our input. So for, let's say this is the inverter. We have in the beginning VDD, then we have 0 until here, we something like this, and again something like this. So this is the typical wave of a CMOS inverter. Here we'd say that the switching is somehow earlier, so it will go quickly and then it stays and then it's pulled down later, but it pulled down faster. So this is important also to notice. So let's take some numerical examples. Assume we have VDD equal to 3.3 volt, VTN equal to absolute VTP equal to 0.4 volt. And let's say that we want everything in the middle. So here V input, V output. We want to switch at 1.1 and at 2.2. Here we have our VDD 3.3 volt. So let's say this. First we will say beta 3n beta and beta 1n equal to V switching high minus VTN square divided by VDD minus V switching point high square. So 2.2 minus 0.4 square divided by 1.1 square, which means about 2.6. For the B side, it will be exactly the same, which means beta 3p over beta 1p equal to 2.6. Someone may ask the value of M2. We have not talked about this. So this is N1, this is N2, this is N3. Now we know that if we want hysteresis, we need N2 to have some value, let's say that equal to N1 or more. What about N2? For N2, this is actually a switch, which we don't want it to be very slow. So as a rule of thumb, we can say that W2 is more than W1, or let's say beta 2 is larger than beta 1. Okay, now we can also take another example that in the case of beta 1 equal to beta 2, in this case we will have V switching point high minus V Tn square equal to VDD minus V switching point high square. This, if we take the square root, this means that V switching point high will equal to VDD over 2, which is our original VM, plus VTN over 2. Similarly, V switching point low equal to VDD over 2 minus VTP over 2. So we can say that if we use similar size, we have a noise margin of VTN over 2 plus VTP over 2, which translates, let's say, VTN equal to modulus VTP equal to VT. So we will have a noise margin equal to VT. And if we want symmetry for both sides, the upper noise margin will be VT over 2 and the lower is VT over 2 also. To summarize, we would like to have usually beta 3 over beta 1 is 1 or more for a Schmitt trigger, because if we have it very small, it is basically a CMOS inverter. Same for beta 2, we can set beta 2 to 2 beta 1. So if beta 2 is 2 beta 1 and beta 3 is 2.7 beta 1 for our VDD equal to 3.3 volt and V threshold is equal to 0.4 volt, we will have V switching point high at 2.2 volt, V switching point low at 1.1 volt. Okay, I wish you like the video. If you like it, please like it and share it. and I would like to see also your comments. Thank you. Bye bye.